All right, so here's your homework from the limit questions that we did yesterday. So again, we're trying using Desmos, or if we're given the graph, could you find the limit that we're looking for? So the first skill that we practiced was this being able to write end behavior as a limit, knowing that limit is what something is approaching. So if I want to know the left hand, how do I write that as a limit again? And be comfortable with limit notation. So limit means LIM. What is x approaching when it's left hand behavior? That's negative infinity. What function are we using? We're just going to call this f at x. So we say the limit as x approaches negative infinity of f at x equals, and what's the answer? And so we learned in the last one we could actually write down this does not exist as it, but as an end behavior we are going to write down infinity or negative infinity in this case. So in this case it's going to infinity. How about the other side? The right end behavior, limit as x approaches infinity of f at x, and the right end is going up. So the right end is going to infinity. Both ends. All right, number 2. Let's be comfortable writing as a limit. Limit as x approaches. Now left would be negative infinity of f at x equals. And the left end kind of looks like it's flattening out to a number. So if I see what's the y coordinate that it's getting closer to, so I count down and I see that answer is negative 3. The right end at limit as x approaches positive infinity. Where's the right end? And it's going to infinity. So one more time, being able to be comfortable writing it in limit notation. So we have the limit as x approaches negative infinity. That's the left. And I want you to notice the left here, not the middle part, but the left is going up. So that's of f at x, and that's equal to infinity. The right end behavior, so the limit as x approaches infinity of f at x equals, and then where's the right end going? And you can see the right end is going down or to negative infinity. So this is more practicing limit notation and knowing that you know how to read the limit and know how to write the limit. All right, number 4. Can you estimate each limit using a table or a graph? And what I did say for the last question is we're going to understand that for these situations, if you can do a substitution and get the answer, so be it. But we are going to do it off a graph and so on. So we're going to open up Desmos, and we're going to do negative 4x plus 3. So if I write down f at x equals negative 4x plus 3, I want to know the limit as the function is approaching negative 2. So what is the value at negative 2? And the other thing I need to know is realize around negative 2, when I look at the function, is there a jump or anything that would have something that's not continuous here that I need to look at? And there isn't. So at negative 2, do we have an answer? So off the graph, I can see that the answer is 11. So for number 4, the answer is 11. Let's look at number 5. So for number 5, the function is x squared subtract 7. And again, if I looked off the graph, I could also just substitute in. So when x is 1, what's the answer? So right around here, x is 1. I see it. So trace along the graph and find 1. And then you can see what the answer is. So off the graph, you can see the answer is, it's a little tricky, is negative 6 off the graph, and when you just plug in. So the limit here is negative 6. And again, I'm looking to see if there's a jump or an asymptote that would affect that answer. But there isn't. It is continuous, and that's the answer. The next one is x cubed. Subtract 7x squared plus 7x plus 15. And again, I'm looking at 3. So when I look at 3, in fact, I can find it right there off the graph. What's the y coordinate when x is 3 and it's continuous around it? Both sides agree that it's getting and approaching 0 for an answer. Number 7. This one is a rational function, so I have to be careful of the asymptote. So f at x equals, and we have a fraction, x subtract 3, and in the denominator 4x plus 4. And I'm looking at -1. So what's happening at -1? And what I notice at -1, and if I type it in, I could definitely see it, that at -1, we have an asymptote. And on one side it goes up, and on the other side it goes down at -1. So because there's an asymptote, what's the answer here? For number 7, we say that the limit does not exist. So far, those are the answers I have from 4 to 7. Looking off a graph to get our limit. All right, number 8. I'm just going to stay on Desmos, and then I'll go back and so you can see my sheet in terms of what answer I'm writing down. So the next one, again, I need to be aware of because it's a rational function. So we have x squared, subtract 4x, subtract 5. We have x squared, subtract 11x, plus 30. So if I look off the graph, I'm looking to see when the limit of x approaches 5. So if I just plug in 5, it's undefined. And I need to look at 5, is there an asymptote or does it approach a number? So if I look here, I'm going to trace along the graph here at 5. And I want you to notice that at 5, there's no asymptote. The asymptote is actually at 6, not at 5. So it kind of looks it, but it's actually at 6 where the asymptote. So at 5, we're actually approaching a number. Now, when I actually get to 5, I want you to notice that there is a hole in the graph. So do you see the hole there? So exactly at 5, there's a hole. So it doesn't exist. But what's the y-coordinate it's approaching from both sides? And so can you see on both sides what the y-coordinate is at that hole? And the y-coordinate at that hole is -6. So from the right and left, it's approaching -6, though when it hits -6, there's a hole. So the limit exists not because of equal, but because it's approaching that y value. And it's approaching the value of -6. All right, the next one. Number 9. So we have x squared subtract same one. Oh, same function completely, so I shouldn't have erased anything. For this one, it's approaching 6, and I think I already alluded to this. When x is 6, there's an asymptote. And so because there's an asymptote, what did I type in wrong here? X squared minus 4x minus 5, x squared on the bottom. There it is. So at 6, there's an asymptote, not at 5. So, and it goes up in one direction, down the other. So why doesn't it exist for number 9? Because at that x value, there's an asymptote. And that's what makes it undefined. If there's a hole, and it's in the middle of a continuous function, meaning that the y value, there's no jump at all with the hole, then the limit exists. All right, number 10, x cubed plus 8. And then x squared, subtract 4x, subtract 24. All right, and I'm looking for, as x approaches 2. So as x approaches 2, what's the y value here? So make sure I typed it in right. So it's x, as x approaches -2. So as x approaches -2, we actually, on the graph, you can see the y value there at -2 is 0. There's no asymptotes, no holes, no jumps, no oscillation. That's the answer. It's the y value there. So the answer there is 0. Number 11. In the numerator, I have x squared, subtract 2x, subtract 3. In the denominator, I have x squared, 4x squared, subtract 20x, plus 24. So if I look at that, I want to know what the value is as x approaches 3. So when I look at 3, what's happening? So here, I'm going to get to 3. I want you to notice at 3, if I could do it, there's a hole. But what's the y value there where it's a hole? Like, what is it from the left? What is it from the right? Look off the graph, count up the squares, and you can see the y coordinate it's approaching from the left and from the right is positive 1. So can you see what's the y value of that hole? And look off the grid. Count up 2 on the grid and look at the scale. That's positive 1. So it doesn't exist there. So it's not equal, but the limit exists because it's approaching that y value. I'm just going to say it over and over again because it's such a new concept. The idea of approaching rather than equals. All right, number 12. X squared subtract 8x plus 16. And then x squared minus x minus 20. And again, this time we're doing it at 0. So I can even actually see it right there at 0. And notice left and right both agree. And what's the y value there? It's negative 0.8. Where'd my pen go? So the answer is just negative 0.8. You can put a 0 there if you like, just to know that we're on the same track. So here are the answers so far, up to 12. All right, let's keep going. Again, I'm mostly going to use Desmos here to show you what the limit is. Oh, I pressed the wrong one here. There it is. So for here, the next one is I need absolute value of x subtract 1, and then the denominator is x subtract 1. And then what I'm looking for is what's happening as x approaches 1. So can you see where positive 1 is for x? What's happening to the graph there? Do you see this jump? So there's a jump at x equals 1. Therefore, the limit does not exist. That's it. Looking off a graph. Next, I have 4 to the x subtract 2 to the x, and then 2x in the denominator. And I want to know what is it as it's approaching 2. So as it's approaching 2, what's the answer? Scroll up here. So can you see off the graph that 2 gives you what y value? And the answer is 3. There's not even a hole there. So the y value is 3. That's the y value it's approaching and what it equals. So you have two concepts. It's approaching 3 and it equals 3. So sometimes there's an and, where it's both, equal and approaching. And that is a calculus definition of continuity. That if something's continuous, the limit and the function value are exactly the same. So what's it approaching and what does it equal? If they're the same, therefore the function is continuous at that number. So that's a definition of continuity. 15, piecewise. So for 1, let's see if we can type in this piecewise. We have I think there's a way to type it in directly. Let's see. I knew there was a way at one time to type in a piecewise here. All right. Let's just go for it. So f at x equals, and we have x cubed. So I'm just going to do a domain restriction. So I'm going to say that that's only true for when x is less than -2. So I'm going to type it in with 2 boxes. So there's 1. And you can see that it's hard to see it, but there it is off the graph. The second one, we're going to call it g at x equals, I'll try f at x. Let's see what it does if I say f at x. So f at x equals 2x subtract 4. It may not like it. Oh, it does. It's fine. So we can still say f at x. But this is for when x is greater than or equal to. And that's greater than or equal to -2. And the greater than or equal to button is right there on the Desmos keyboard. And then use the fancy parentheses. So if you type it in the way I type it in, I want you to see the graph that's created. So this is a piecewise. So one piece is the purple and the other piece is the red, and they connect to make the graph. And then it says what's happening at -2. So look at the purple. What's happening at -2? If I look at the red, what's happening at -2? And do they agree what the y coordinate is right there? So even though when I look at it, I see kind of a hole, but I don't want to know what it's equal to. On the red, it actually does equal it. So if I take the red, I can get an answer right there. But the purple, there's a hole. So there's a point, and then there's a hole under the point. But what I'm looking for is the y coordinate. Is it approaching the same y coordinate? And the answer is yes. And the answer is -8. Looking off the graph. All right, now some trig functions. So I want to look off of secant x. For this one, it's a little trickier off the graph when it's a radian that gives it. At 0, I can do it. So at secant x, what's happening at 0? So I'm going to press home, and I want you to notice at 0, the answer is +1. There's our answer. That from the right and left, and it's continuous because the limit and the function value are equal to the same number. Number 14. No, we're at number 17, negative tangent x. So type in negative tangent. See, here's a radian. So it's going to be tougher to find the radian off there. I could try to change the scale to radians, but honestly, I'm just going to do a substitution. So 3 pi over 2. And I want you to note it's undefined. Now, what does that mean off this graph at 3 pi over 2 if it's undefined? That means there's an asymptote there. And at that asymptote, the limit is undefined. So it doesn't exist. The next one, 4 sine x. And I'm looking at pi over 2. So again, it's a little trickier here. So when it's a radian like that, pi over 2, I'm just going to type it in. So at pi over 2, what's the y value, or is it undefined? So I want you to notice that this wave is continuous. There's no asymptotes for a sine. And at pi over 2, the y value in this case is 4. Done. That's the limit. And the definition, again, of something that's continuous is understanding the limit and the function value has the same answer. So you can have a limit, but the function doesn't have a value. You could actually have the other way around as well. So where are we at? Number 19. Type this in with me. It's good practice. So f at x equals 3 cosine, and then we have parentheses pi over x. So do you see it oscillates around 0? That oscillation up and down means it does not exist. Number 20. The function is sine x plus pi. And then the question is, it's continuous, no asymptotes or no oscillation like that that's like heavy around a number. And it says when x approaches negative pi. So I'm just going to type in negative pi. And see that the y value there is 0 at negative pi. So that's what the answer is. And then 21 is 4x over tan x. And again, I'm looking for at pi over 4. So at pi over 4, do you recognize that number? That y value of that number is actually pi. 3.14 and so on. What you're looking at is the value of pi. So let's just go back to this so you can see my answers. And your homework part here is done. So here are my answers from like 13 to 21. So make sure that you have same answers. So what was the skill we were working on? Off a graph, can you find the value of a limit? Do you know what a limit is? Do you understand the idea of approaching rather than equals, even though sometimes they give you the same answer? So that's what we're practicing, finding limits off a graph. Our next lesson is going to be finding limits algebraically, I think, or maybe one-sided. So until next time, I'm super proud of you that you're doing your work. I hope you're learning something. The questions you have, I want to answer too. So Mr. G Math over and out, and until next time.